Okay, after a good long break, I'm back and let's read it and let's try to finish up to which the first week will be. So let's go back. Okay, we are on the map class. This section introduces another generic class called map, which is conceptually similar to a dictionary. A dictionary allows you to look up a word to find its meaning. A map is a generalization of this idea that provides an association between an identifying tag called a key and an associated value, which may be much larger and more complicated structure. In the dictionary example, the key is the word you're looking up and the value is its definition. Maps have many applications in programming. For example, an interpreter for a programming language needs to be able to assign values to variables, which can then be referenced by name. A map makes it easy to maintain an association between the names of a variable and its corresponding value. When they are used in this context, maps are often called symbol tables, which is just another name for the same concept. The structure of the map class, as with the collection class introduced earlier in this chapter, map is implemented as a template class, then must be parameterized with its value type. For example, if you want to simulate a dictionary in which individual words are associated with their definitions, you can start by declaring a dictionary variable as follows: map of string named as dictionary. Similarly, if you use a map to store values of floating point variables in a programming language, you would start with the following definition: map double. These definitions create empty maps that contains no keys and values. In either case, you would subsequently need to add key value pairs to the map. In the case of the dictionary, you could read the contents from a data file. From the symbol table, you could add new associations whenever an assignment statement appeared. It is important to note that the parameter for the map class specifies the type of the value and not the type of the key. Oh, okay. In many implementations of collection classes, including, for example, the one in the standard template library and its counterpart in the Java class, you can specify the type of the key as well. The map class used in this book avoids considerable complexity by insisting that all the keys be strings. Strings are certainly the most common type for the keys, and it is usually possible to convert other types to strings if you want to use them as map keys. For example, if you want to use integers as key, you can simply call integer to string function on the integer version of the key and then use the resultant string for all the map operations. The most common methods used with the map class appear in table 4-5. Of these, the ones that implement that fundamental behavior of the map concept are put and get. So size returns the number of key value pairs contained in the map. Is empty returns true if the map is empty. Put key value associates the specified key and the value in the map. If the key has no previous definition, a new entry is added. If a previous association exists, the old value is discarded and replaced by the new one. So basically the put is used for adding a new key value pair and also to change. So it's for the both. Get key returns the value currently associated with the key in the map. If there is no such value, gets generates an error. Remove key removes key from the map along with an associated value. If key does not exist, this leaves the map unchanged. Contains key checks to see whether key is associated with a value. If so, this returns true. If not, it returns false. Clear removes all the key value pairs from the map. Iterator returns an iterator that makes it easy to cycle through the keys in the map. Cycle through the keys in the map, like it's the same thing as in the dictionaries in Python. Put method creates an association between a key and a value. Its operation is analogous to assigning a value to a variable in C++. If there is a value already associated with the key and the old value is replaced by the new one, the get method retrieves the value most recently associated with a particular key and therefore corresponds to the act of using a variable name to retrieve its value. If no value appears in the map for a particular key, calling get with that key generates an error condition. You can check for that condition by calling the contains key method, which returns true or false depending on whether the key exists in the map. A few simple diagrams may help to illustrate the operation of the map class in more detail. Suppose that you have declared the symbol table variable to be a map double, as you saw earlier in this section. That declaration creates an empty map with no associations, which can be represented as the following empty box. Once you have the map, you can use put to establish new associations. For example, you were to call symbol table dot put pi with 3.14959. The conceptual effect would be to add an association inside the box between the key pi and the value 3.14159 as follows. If you then called symbol table dot put e 2.71828, it will add another one. Now if you use get to retrieve these values, you will say get pi and it will return that, and if you do put pi 3.2, now it will change the value of the pi. At this point, calling symbol table dot contains key pi would return true. By contrast, calling symbol table key contains key x would return false. Using maps in an application. If you fly at all frequently, you quickly learn that every airport in the world has a 3-letter code assigned by the International Air Transport Association. For example, John F. Kennedy Airport in New York City is assigned the 3-letter code JFK. Other codes, however, are considerably harder to recognize. Most web-based travel systems offer some means of looking up these codes as a service to their customers. Suppose that you have been asked to write a simple program that reads a 3-letter airport code from the user and responds with the location of that airport. The data you need is in the form of a text file called airportcodes.txt, which contains a list of the several thousand airport codes that IATA has assigned. Each line of the file consists of a 3-letter code and equals sign and the location of the airport. If the file were sorted in descending order by passenger traffic in 2009 as compiled by the Airport Council International, the file would begin with the lines, given the map class, the code for this application fits on a single page as shown in figure 4.6. The program makes it possible from the user to see the following sample run. Okay, so this and then this. Looks like it has a city, it has a state, and then the country. Yeah, something like that. Okay. Let me just check how much work do I have tomorrow. Seems like just 2 hours again. Fine. Tomorrow's 2 hours. Only if it's different. Okay. Let's go back. So that's how the file looks like. The program to look up 3-letter airport codes. So we will do a read code file. First of all, in the int main, we have a map of string, which is airport codes. Reader code file airport codes. While true, cout airport code, string code, convert to uppercase, get line. If code is equals to nothing, break. If the airport codes don't contain key code, then return the. Otherwise, you will say there is no such airport code. Read coder file, it will take the map from us. If stream in file, because we are reading from a file, not off stream. In file dot open, we open that specific file. If the in file dot fail, then we put the error can't read the data file. While true, string line, get line, in file line. If the infile dot fail, break. If the line dot length less than 4 and the line 3 not equals to equals illegal data file line. String code, convert to uppercase, line dot is substring 0 till 3, map dot put code, line dot substring 4. Oh, from the 4 till the end. Yeah, makes sense. Okay, that's nice. Then we just use infile.close to close it. Okay. Maps as associative arrays. The map class overloads the square bracket operators used for array selection so that the statement map square brackets key equals to value acts as shorthand for map.put key comma value. And the expression map square brackets key returns the value from map associated with key in exactly the same way that map.getKey does. While those shorthand forms of the put and get methods are certainly convenient, using array notations for maps is initially somewhat surprising, given that maps and arrays seem to be rather different in their structure. If you think about map and arrays in the right way, however, they turn out to be more alike than you might at first suspect. The insight necessary to unify these two seemingly different structures is that you can think of arrays as structures that map index positions to elements. For example, the array used as an example, the key 0 into the value 9.2 and like that. So that's the key is basically the integer indexes, and then you map it with the values, and values can be anything. Conversely, you can think of a map as an array that uses strings as index positions, which is precisely what the overloaded selection syntax for the map class suggests. Using array syntax to perform map-like operations is becoming increasingly common in programming languages beyond the C++ domain. Many popular scripting languages implement all arrays internally as maps, making it possible to use index values that are not necessarily integers. Array implemented using maps as their underlying representation are called associative arrays. Oh, so some arrays are actually implemented using maps under the hood, so they are called associative arrays. The lexicon class. Okay, we are done with the map class. We were done with the queue and the stack. Now let's move, and we were done with the grid and the array or vector before. Let's move to the lexicon class. A lexicon is conceptually a dictionary from which the definition, oh, it was looking like a lexicographical order, so it's something related to an actual dictionary. From which the definitions have been removed. Given a lexicon, you can only tell whether a word exists. There are definitions or values associated with the individual words. The structure of the lexicon class. The lexicon class offers two different forms of the constructor. The default constructor creates an empty lexicon to which you can add new words. In many applications, however, it is convenient to provide the constructor with the name of the data file that contains the word you want to include. For example, if the file englishwords.dat contains a list of all the English words, you could use that file to create a lexicon using the following declaration. Lexicon, and then you put English, and then you just say englishwords.dat. Oh. So you created a lexicon from that file named as English. The implementation of the lexicon class allows these data files to be in either of two formats. It can either be in the text file, in which the words appear in any order, one word per line, a precompiled data file that mirrors the internal representation of the lexicon. Using precompiled files such as the DAT files is more efficient both in the terms of space and time. Unlike the classes presented earlier in this chapter, lexicon does not require a type parameter because a lexicon doesn't contain any values. It does, of course, contain a set of words, but the words are always strings. Oh, so lexicon always contains strings. It cannot contain integer or anything else. So that's why it doesn't have a type parameter to it. The methods available in the lexicon class appear in the table 4 to 6. The most commonly used method is contains word, which checks to see if a word is in the lexicon, assuming that you have initialized the variable English so that it contains a lexicon of all the English words. You could see if a particular word exists by writing a test such as the following: if English.contain words parenthesis word. And because it is useful to make such tests in a variety of applications, you can also determine whether any English word begins with a particular substring by calling English.contains prefix. A simple application of the lexicon class in many word games such as the popular Scrabble crossword game, it is critical to memorize as many two-letter words as you can. Two-letter words. Because knowing the two-letter words makes it easier to attach new words to the existing words on the board. Given that you have a lexicon containing English words, you could create such a list by generating all the two-letter strings and then using the lexicon to check whether which of the resulting combinations are actually words. As you will discover in the section 4.8, it is also possible to solve this problem by going through the lexicon and printing out the words whose length is 2. Given that there are more than 100,000 English words in the lexicon, only 676, 26 plus 26 combinations of two letters, the strategy used in figure 4.7 is probably more efficient. Size, again, used to find the number of words in a lexicon, is empty, returns true if the lexicon is empty. Add word adds a new word to the lexicon. If the word is already in the lexicon, this clause has no effect. Each word may appear only once because it's a set of words. All words in a lexicon are stored in lowercase, so the lexicon sounds like a set actually in Python. Add words from file name. Add all the words in the named file to the lexicon. The file must either be a text file, in which the case the words are listed on separate lines, or a pre-compiled data file in which the contents of the file match the internal structure of the lexicon. The add words from file method can read a pre-compiled file only if the lexicon is empty. Contains words word, returns true if the word is in the lexicon. Contains prefix, returns true if any of the words in the lexicon starts with the specified prefix. Clear will remove all the elements from a lexicon. Iterator returns an iterator that makes it easy to cycle through the words in the lexicon. Okay. Now the program to display all two letters English words. Oh. So we are reading an English words.dat file, and we are making a lexicon out of that. We are doing string word XX. For the character C0, A till Z, C0 plus plus, word 0 will be C0. Then that's the constant. Now we will keep on changing the word of 1 to the C1. If English contains word, then we see out the word because that word needs to be possible. We can't say that AA is a word, but at is a word, and if is a word, or is a word. So those those two letter words should actually make sense. Why are lexicons useful if the map already exists? If you think about it, a lexicon is in many ways just a simplified version of a map in which you ignore the values altogether. It would therefore be easy enough to build most of the lexicon class on the top of the map class. Exactly. This is what a set is, because set also contains the keys inside it. Lexicon also contains the keys inside it. The only thing which is different is lexicon always contains strings inside it, but a set can contain anything. Adding a word to the lexicon corresponds to calling put using the word as the key. Calling whether a word exists corresponds to calling contains key. Given that the map class already provides most of the functionality of the lexicon, it may seem odd that both classes are included in this book. When we designed the ADT library, we chose to include a separate lexicon class for the following reasons. Not having to worry about the values in a map makes it possible to implement the lexicon in a more efficient way, particularly in terms of how much memory is required to store the data. Given the data structure used in the lexicon implementation, the entire English dictionary requires approximately 350,000 bytes. If you were to use a map to store the words, the storage requirements would be more than 5 times greater. The underlying representation used in the lexicon makes it possible to check not only whether a word exists in the lexicon, but also to find out whether any word in the lexicon starts with a particular set of characters. The lexicon representation ensures that the words remain in alphabetical order. Although these characteristics of the lexicon class are clearly advantageous, it is still somewhat surprising that these reasons focus on what seem to be the implementation details, particularly in light of the emphasis of this chapter places on ignoring such details. By choosing to include the lexicon class, these details are not being revealed to the client. After reading the justification for the lexicon class, you have no idea why it might be more efficient than the map class for storing a list of words, but you might well choose to take advantage of that fact. Okay, probably the last class, called the scanner class. We are not sure if it's the last one. But we'll see. So, The scanner class. The last of the abstract data types introduced in this chapter is the scanner class, which provides a useful tool for dividing up a string into meaningful units that are larger than a single character. I know that string scanner actually. That string. Okay, larger than a single character. After all, when you read text on a page, you don't ordinarily pay much attention to the individual letters. Your eye instead group letters to form words, which it then recognizes as independent units. The scanner class does much the same thing. It divides an input string into its component tokens, which are ordinarily either a sequence of consecutive alphanumeric characters, letters, or digits, or a single character string consisting of a space or punctuation mark. For example, if the scanner were initialized to extract tokens from the string, this line contains 10 tokens. Successive calls to the scanner package would return those 10 individual tokens as those by the boxes on the following lines. This space, line, space, contains space. It's basically working like a split function in the Python. Using the scanner class, when you want to use the scanner class, you typically go through the following steps. Create a new scanner object. As with the abstract data types introduced earlier in this chapter, your first responsibility when using a scanner is to declare a new scanner object like this: scanner. All the classes' name starts with the uppercase letter, by the way. The scanner object, which is called scanner in this example, keeps tracks of all the state information it needs to know, the order in which the token should be delivered. The methods in the scanner class all operate on a particular scanner object, which means that you must always specify scanner as a receiver in any calls that you make. Initialize the input to be scanned. Once you have a scanner instance, you can then initialize your scanner input by calling scanner.setInput_str, where str is the string from which the tokens are scanned. Alternatively, if you want to read tokens from a file, you can put a file inside it. So scanner.setInput is just taking the string or the file from which you are going to read the tokens. Read tokens from the scanner. Once you have initialized the scanner input, you can process each of its tokens individually by calling scanner.nextToken for each token in the input. When all the tokens have been consumed, the method scanner.hasMoreTokens returns false, which means that the standard idiom for iterating through each token in turns looks like: while scanner.hasMoreTokens, string token equals scanner.nextToken. Do something with the token you have found. Maybe just print it. So, because it is often easier to check for a sentinel value, the next token method returns the empty string if you call it after the last token has been read. You can use the same scanner instance many times by calling setInput for each string you want to split into tokens. So you don't need to declare a separate scanner for each string that you have. Okay, one scanner works. So like if you make one scanner and ask user for input file, that's the function, I guess, is it? Okay. So we do scanner.setInput and we set a file in this case. While the scanner has more tokens, we read for the next token. If all alpha word and English contains words, is all alpha is basically going through the string length and checking if it's alpha, returns false. If it's not alpha, okay. Setting scanner options. As you can see from table 47, most of the methods in the scanner class allow clients to redefine what character sequences count as individual tokens. By default, the scanner recognizes only two classes of tokens: sequences of alphanumeric characters and single characters that fall outside the numeric set. Depending on the application, clients may want to change this interpretation. For example, a C++ compiler has to recognize numbers like 3.14159.265 and quoted strings like hello world as single tokens. A browser must do the same with the tag like p tag starts a new paragraph, b as switch to a bold face that are part of the hypertext markup language HTML in which most web pages are written. In many contexts, including both the compiler and the web browser, it is useful to ignore white space characters, space, tabs, and end of the line markers because these characters serve only to separate tokens and have no semantic value. So basically, they don't really make sense. These capabilities are incorporated into the scanner class as an option settings. You enable a particular option by calling a method with an argument that specifies the behavior you want. To enhance readability, the scanner class defines a set of enumerated type constants whose names describe as closely as possible exactly what the option does. For example, if you want to ignore white space characters, you can call scanner.setSpace option scanner ignore spaces. So you need to read more about those. The names of the constants used to set each option are described in table 47 along with the method to which those constants apply. The scanner class also exports a method called saveToken that comes in handy with a variety of applications. This method solves the problem that arises from the fact that you often don't know that you want to stop reading a sequence of tokens until you have read the tokens that follow that sequence. Unless your application is prepared to deal with the new token at that point in the code, it is convenient to put that token back in the scanner stream where it can be read again when the program is ready to do so. Okay, so save token is used to save the tokens temporarily so that we can start reading the token again after a while. Okay. Okay, we are on iterators. Iterators, the two-letter.cpp program introduced earlier in this chapter computes a list of all two-letter words by generating every possible combination of two letters and then looking up each one to see whether then what that two-letter string appears in the lexicon of English words. Another strategy that accomplishes the same result is to go through every word in the lexicon and display the words whose length is 2. To do so, all you need to do is the same way of stepping through each word in a lexicon object one at a time. Stepping through the elements of a collection class is a fundamental operation that each class must provide through its interface. Moreover, if the package of collection classes is well designed, clients should be able to use the same strategy to perform that operation. No matter whether they are cycling through all the elements in a vector or a grid or all the keys in a map or all the words in a lexicon. In most modern software packages, including the libraries ADTs used in this book and the standard template library on which those classes are based, the process of the cycling through the elements of a collection is provided through a class called iterator. Each abstract collection class in the library, with the exception of stack and queue, for which being able to process the elements out of order would violate the LIFO or FIFO order that defines those type, exports its own iterator class, but defines that class so that all iterators behave in the same way. Once you learn how to use an iterator for one class, you can easily transfer that knowledge to any of the other classes. Methods exported by the scanner class. Set input str sets the scanner input source so that the new tokens are taken from the string str. Any unread tokens remaining from the preceding call to set input are discarded. Okay, let me check one thing. Okay. So, 1 second, I need to reply. So basically, I had a class and it got cancelled. Very depressing. Okay, let's get back to work. So, wait 1 second. This is that. Okay, so the methods exported by the scanner class. Set input str sets the scanner input source so that new tokens are taken from the string str. Any unread tokens remaining from the preceding call to set input are discarded. Set input stream. So it just sets the scanner input source so that new tokens are taken from the input stream. Opening and closing the input stream are the responsibility of the client. As with the string version of this method, any unread tokens from a previous call are discarded. Has more tokens. Returns true if the scanner contains additional tokens. Next token reads the next token from the input source, either a string or a file, and returns it as a string. If no more tokens exist, next token returns the empty string. Save token stores the specified token in the private state of the scanner so that it will be returned the next time the next token is called. Get space option allow the client to control whether white space characters, spaces, tabs, and end of the lines are returned as single character tokens or skipped entirely. The option parameter must be one of the following constant names: preserve spaces, ignore spaces. Get number option allow the client to control whether the numeric strings are recognized as single tokens. The option parameters must be one of the following constant names: scan numbers as letters, scan numbers as integers, scan numbers as reals. By default, digits are considered just like letters, and the other options allow the scanner to read a complete number. Set string option get string option allows the client to control whether quoted strings are recognized as single tokens. The option parameter must be one of the following constant names: scan codes as punctuations and scan codes as strings. By default, quotation marks acts like another punctuation mark. If scan codes as string is in effect, a quoted string is treated as a single token. Set bracket option allows the client to control whether HTML tags enclosed in angle brackets are recognized as single tokens. The option parameter must be one of the following constant names: scan brackets as punctuation, scan brackets as tag. Nice. By default, angle brackets acts like one of the another punctuation marks. If the scan brackets as tag is in effect, The entire tag, including the angle brackets, is treated as a single token. The standard iterator pattern. The general pattern for using an iterator is illustrated by the following code fragment, which iterates over every word in the now familiar lexicon of English words. Lexicon iterator iter. English dot iterator. While iter has dot next, iter dot has next. String word equals iter dot next. Code to work with that word. The iterator method with the method in the lexicon class returns an iterator that provides each word in the lexicon one at a time. The iterator class itself is defined as a nested subclass within lexicon. So its full name is lexicon : iterator. Okay, because every class has its own iterator inside it. Every class has its own iterator class inside it. Really nice. And this is how we call another class inside a class: lexicon : iterator. The first line of this example therefore applies the iterator method to the lexicon stored in a variable English and then stores the resultant iterator object in the variable iter, which has been suitably declared with the full name of its type. Once you have the iterator variable, you then enter a loop that continues as long as the iterator has more elements to process. The has next element returns a boolean value that indicates whether any additional elements remain, which is exactly what you need for the condition in the while loop. Inside the loop, the next method returns the next element in the collection. In this example, calling iter.next returns the next word from the English language lexicon, which is then stored in the string variable word. The code that needs to go into the body of the loop depends, of course, on what you are trying to do. If, for example, you want to list all 2-character English words using the iterator model, the code to do so will look like this. So you make the iterator first of all, lexicon : iterator iter equals English.iterator. You put the name of that lexicon for which you want to make the iterator, so English.iterator parenthesis, while iter.has next, string word equals iter.next. If the word.length is equals to 2, then you see out the word, otherwise not. The type of the value produced by the next method depends on the class in which the iterator is created. In the map and the lexicon class, next always returns a value of the type string. In the array and the grid class, next returns a value whose type matches with the base type of that collection. Thus, an iterator of an array int will produce values of type int, and the iterator of a grid char will produce values of type char. The for each idiom, even though the iterator pattern introduced in the preceding section takes a few lines of code, I have discovered over the years that the details of the iterator mechanism get in the way of understanding the purpose of the iterator, which is simply to step through the elements of the collection one at a time. If you were trying to express the algorithmic function of an iterator in English pseudocode, you would want to write something like this: for each element in a particular collection, process that element. So that's another kind of loop we have. That's the for each loop.